I'm Jim McLaughlin, and I'll be talking about the energy expenditure lecture today and the elements that are involved in this. Work physiology is the study of the functions of humans affected by muscular work and stresses. This will be our focus. The work physiologist then devise work systems that allow individuals to accomplish their work without developing excessive fatigue on a day-to-day basis. Notice that it's underlined without developing excessive fatigue, so that a person who begins work on Monday will have the same level of energy on Friday, resulting in recovery over the weekend and then coming back in on Monday and repeating it all over again. This is really the drive of this whole lecture and the importance of work physiology. The body's physiologic responses, the musculoskeletal and cardiovascular. We know something about the musculoskeletal efforts in this, and one of the things to cross over here is to look at aspects of fatigue, and one of the things that I try to enforce is the aspect of safety and ergonomics, that there is a crossover point, that these are not silos, that if you work to a point in which you become very fatigued in what you do, there's a higher likelihood of an accident occurring, such as a slip, a trip, or a fall, running into somebody, doing serious injury or damage to yourself or to others. And that's how this plays into this. The cardiovascular aspects include heart rate, body temperature, blood pressure, respiration, oxygen consumption, and metabolite concentrations. In terms of body temperature, there are several ways to get this information: oral, rectal, and skin. Oral temperatures sometimes can be erroneous, especially if the person's had been sipping some cold drink or a hot drink. They can throw the temperature off. Skin temperature can be affected based on the wind going across the skin and the variances there in different parts of the body involved in vasoconstriction, vasodilation. Rectal temperatures tend to be the most reliable. The challenge there, of course, is getting people to accept the condition in which they would have their core temperature measured in this way. Often called a SAMI, which is a socially acceptable measuring instrument for such things, and it continues to be a challenge today. Other options include a thermistor, where you can swallow a temperature probe. The problem is that it's somewhat costly, and the researchers like to get it back, have it retrieved, and it relies upon the subject to be able to do that for them, and you can imagine how these situations become somewhat awkward in trying to get that data. Other aspects, ventilation rate, in looking at respiration rates for breathing normally in and out, or maximum expiratory volumes, become a role in terms of the person's rate of breathing and labored breathing once they become too fatigued. And then metabolite concentration is something to look at in terms of the saliva, the blood, and the urine. Remember, saliva is an exudate of blood, so often things can be measured in the saliva, such as cortisol, to measure stress, and so on. The ergonomist interest in work physiology really looks at the demands on workers. The theory is that workers should not exceed 50% of their energy expenditure capacity during the workday to avoid becoming physiologically strained during the workday. However, for a margin of safety, the worker should not exceed 33% of their expenditure capacity for the workday. So this is the safety factor that goes into play, and whenever people are asked about this, the answer is 33%, not 50%, just to give you that margin of error for those people that may not be physically fit and so on. How do you do this to be assured of that? We'll get into that in a little bit, but part of it's heart rate monitoring, heart rate recovery, and so on. Anaerobic threshold. This is a point in which lactic acid from anaerobic glycolysis begins to accumulate in the blood at levels above the basal rate of lactic acid production. For untrained individuals, The anaerobic threshold, or AT, occurs at 50% of the aerobic capacity of the VO2 max. For highly trained individuals, this can occur as high as 85%. So it's important that we start looking at this to avoid any lactic acid accumulation, that we understand anaerobic thresholds, which is obviously going beyond the ability to supply oxygen to the muscles in their work activities. Energy and energy sources. Remember that the body gets energy for the muscles to perform physical activities through two processes. One is the aerobic, and that is the presence of oxygen. The other is anaerobic, the absence of oxygen. The application is to discern which jobs or job elements require high work intensity and develop strategies for recovery from oxygen deficit. So many of you have probably experienced the idea of being able to perform exercise when you have enough oxygen, and also gotten involved in activities where you had labored breathing. An example would be a sprint, where you would run very, very hard in, let's say, 100 yards or so, knowing that you weren't replacing the oxygen as it was being used in terms of cardiovascular demands. And what happens is that that oxygen debt that occurs then is repaid once you complete that 100-yard dash. So energy supply during rest, your basal metabolism, 2/3 of the energy consumed by the body is supplied by fat and a smaller percentage by carbohydrates. Oxygen consumption level is between 1/5 and 1/3 of a liter of oxygen per minute. I'll hold you responsible for that in knowing that we're looking at 2/3 of the energy consumed comes in through fat and by carbohydrates. But more important is that if we're looking at an average-sized individual, when it comes to basal metabolism, that we're looking at about a 1/5 to 1/3 of a liter of O2 consumed per minute. Energy supply during work. Oxygen consumption profile for prolonged workout goes like this. Oxygen does not start at zero, as most of you know, but is at resting rate and returns to resting rate after recovery from work. Initial O2 demands do not start immediately, and as a result, an oxygen deficit occurs. Steady state occurs in 3 to 5 minutes after work, and a deficit is repaid during the resting state. So some of you already know this, is that if you're as you're sitting there in class, but if I were to ask you to get out of your chair and to run up 3 flights of stairs and to come right back down and to sit in your chair, that your heart rate is going to be much elevated after going up and down the 3 flights of stairs than it is right now. But eventually the heart rate returns back to the resting level, and the key is to look at where you recover in terms of heart rate, and also to understand that when you're looking at heart rate over time, that into a work routine, that usually about 3 to 5 minutes into any particular routine, that you've found some steady state of the heart rate to occur. O2 consumption, recovery time is generally much longer than the time it took to build up to a steady state. Intensity, activity, and fitness of the worker affect recovery, which can take from a few minutes to an hour. 80 to 90% of recovery takes place in the first few minutes of the recovery period. This assumes a normal work period and a recovery period. If you have really pushed yourself to the limits, then you will see a much longer recovery time in terms of getting the heart rate back down to base levels. Prolonged work, continuous work, typically involves submaximal efforts for several hours. The fuel sources are carbohydrates and fats, known that when the glycogen stores are depleted, fats are the main source of fuel. This is certainly true for those that run long distances or work long hours, physical labor and so on, that fat tends to be a fuel of choice. Lactic acid does not accumulate because you're not building up an oxygen debt, but anaerobic glycolysis is not needed during steady state work activities, meaning that as you work and the heart rate increases, you're allowed a certain recovery period to get that heart rate back down to baseline. So intermittent work then consists of sustained effort for short periods of time followed by periods of rest. Levels of exhaustion are achieved before the cardiovascular system reaches a steady state condition. In other words, intermittent work would be something like a period of physical labor, let's say digging a trench in a ditch, or perhaps moving a loaded wheelbarrow of soil from one point to another uphill, and so on. Major food fuel during intermittent work is carbohydrates. Fat plays a minor role. Proteins are negligible. Energy supply is anaerobic. Lactic acid does come about. There's a soreness in your muscles. And oxygen consumption continues to increase until the maximum is reached or exhaustion occurs. Respiration rates, the process of exchanging carbon dioxide and oxygen between the body and the environment. Higher altitudes allow for partial pressure of oxygen to be lower, and its uptake is reduced. That's one of the reasons why if you go to a place like, let's say, Denver, Colorado, which is about a mile above sea level, over 5,000 feet, 5,280 feet to be exact, that your breathing is to be more labored in that Why? Because the partial pressure of that oxygen is less, and as a result of that, the oxygen exchange rates with your tissue while working is much greater. Note that the percentage of oxygen concentration at any altitude above sea level is the same as that at sea level, but it's really dealing with the barometric pressures that are different. So it's not like you have less oxygen that you're dealing with a reduced partial pressure, and the exchange rate between the oxygen and the CO2 are more labored because of that. The carbon dioxide is highest in the tissues and lowest in the lungs. For oxygen, it's just the reverse. At sea level, the barometric pressure of dry air is assumed to be 760 millimeters of mercury. There is 20.93% of oxygen in the air. The partial pressure of oxygen, when you calculate it with the barometric pressure, is 159 millimeters of mercury. Then if you were to calculate carbon dioxide, it's at 0.3 millimeters of mercury. The numbers come out in these calculations to give you much lower values, as you would see with the oxygen. And you know that nitrogen, the majority of the percentage of air composed of nitrogen, and I would ask you to do this particular calculation, looking up what the percentage of nitrogen is in the air, multiplying it times the barometric pressure of 760, and your answer comes out to be 600 millimeters of mercury. Partial pressure then from expired air, for O2 it's 116, for nitrogen 565, for carbon dioxide 32, and for water vapor, water in this case 47 millimeters of mercury. So standard temperature and pressure dry, this is a standard combination of measurements that are made when reporting gas volumes. However, they can change based upon altitude, based on temperature, and so on. So your body temperature, pressure saturated, this is the actual measurements that are needed when you need to have barometric pressure reported and converted to the standard temperature pressure dry values. The ambient temperature pressure saturated, this is the value of samples after they have been stored. Temperature and pressure must be reported and compared to the standard temperature pressure dry. So we're all dealing with the same numbers after the adjustments have been made. Things you should know: factors affecting gas exchange between oxygen consumption and CO2, gas transport right down to the alveoli, the circulatory system, and the heart is a pump. So for example, the amount of blood in liters per minute ejected into the main artery by the left ventricle per unit time is our cardiac output. It is a product of stroke volume times heart rate. So if I were to ask you what the stroke volume would be, know that you would need the components of cardiac output and heart rate in order to determine the amount of blood per beat that occurs. And the stroke volume then is the volume of blood in milliliters per minute per heartbeat that's ejected from the left ventricle during a ventricular contraction. So you can just simply play with the math right here to determine heart rates, stroke volumes, and cardiac output by having this information and determining outcomes. At rest, the cardiac output is 5 to 6 liters per minute. I would expect you to remember that. During heavy work, it's about 5 times that amount, between 25 and 30 liters per minute. This is for an average size individual, about 157 pounds or so. The blood volume is approximately 5 times higher, obviously, when going from rest to heavy work. And this is scalable, especially if you're looking at a larger individual or a smaller individual in terms of the amount of blood per minute. So if we look at the correlation between resting cardiac output and body surface area, this index of cardiac output per minute per square meter of body surface area, if we looked at this issue here, about 3.2 liters per meter squared. Our cardiac index is our cardiac output at rest. So if we have 3.2 times the body surface area, if we used me as this example for illustrative purposes, then we determined earlier that this was the body surface area times the amount of blood that's moving at rest. We find that we have 3.2 times 2.32, which equals 7.4 liters per minute at rest. So approximately, what would this be at work? You simply need to just multiply that number about 5 or so, which takes me up to about 35 to 40 liters per minute while working. So the collective chemical processes, the conversion of foodstuffs and oxygen into mechanical work and heat. Our basal metabolism, I expect you to remember this, is the rate of metabolic activity of a subject after 12 hours fasting, 8 hours of resting. The basal rate is generally considered the level of energy expenditure required to keep an individual alive and functioning, but not performing any external work. So it's just your resting rate. Remember that basal metabolism is never negative, and it's never zero. It's always going to be positive. So the basal metabolism then, 1/5 to 1/3 of a liter of oxygen consumed per minute, or converting that to about 1 to 1.5 kilocalories of energy expenditure per minute. Calorimetry, the process of measuring the heat generated by an energy source then. If we looked at direct calorimetry, the measurement of heat generated by a person in a box chamber, for example, is one of the most exact ways of doing this in terms of heat exchange to do it. But the problem is convenience and cost are at odds with each other there. So a lot of people do it indirectly. And this would be the measurement of metabolic rate, usually by oxygen consumption. And the type of instrument that's used here would be an oxylog, a portable instrument that would be fastened to the mouth and nose of an individual working to be able to pick up the indirect calorimetry of measurements. Prediction of metabolic rates then. Major advantages: you don't have to interfere with the worker's job, and it can be used in the design stage of particular jobs. What do you need? Obviously, the oxygen demands of an individual. The job tasks are estimated from relationships between task and corresponding metabolic rate. Every task has to be well defined, and the analyst must be knowledgeable in the types of data required for the predictive method. There are a number of books that are available that would give you tables on energy expenditure that would consider an average size individual and the amount of kilocalories or O2 consumed on the basis of the work being performed. Accuracy can be enhanced by use of checklists and training. The two most convenient methods are tables, as I mentioned, the International Standards Organization, and also Kodak has these in their books and schematics. There are other references, such as the National Institute for Occupational Safety and Health and the American Conference of Governmental Industrial Hygienists. The physical work capacity is the maximum capability of the physiologic systems to produce energy for muscular work. This can be defined by specific muscle groups or activities, whole body activities. When we look at aerobic capacity, we look at the maximum level of oxygen uptake in liters per minute or milliliters of oxygen per kilogram body weight per minute. For the females, it's about 70 to 75% of that of males. As I discussed earlier, this is about the cross-sectional area of muscles and males versus females, where the males' cross-sectional area are greater than that of females, and as a result of that, you're going to have this scalable issue where the females are usually going to find in just about every category in terms of strength, including aerobic capacity, at about 2/3 that of males. The peaks for VO2 max between 18 and 25 years of age and deteriorates as you go up from there. The aerobic capacity assessment methods then, we have our direct. These are workloads to tax the cardiovascular system and oxygen update to their limits. The maximum VO2 should occur at maximal heart rate approximately 220 minus your age. The advantage is accuracy. The disadvantage is a risk for injury when you're going for these maximum limits. Indirect, you can do regression calculations, and you can also look at nomograms. Astrand and Rodal have several books that they published together that get involved with age correction factors and so on to give you a much more accurate readout for aerobic capacity. One of the advantages is that it is easy to use once you're trained in how to do it. The disadvantage is obviously you're going to need some equipment for heart rate monitoring and oxygen consumption, as well as subject consent to gather such data. A step test is one of the alternate methods for estimating VO2 max. One of the popular tests that are used, particularly among physical therapists and occupational therapists, is a step test. It's easy, has low cost, it is portable. They use the following equation that you can see here for VO2, where we have the frequency of steps per minute, we have the height of the steps, we have the steady state oxygen consumption, and this is in milliliters of per kilogram per minute. And then we want to convert VO2 into liters per minute. We just take the mLs times the body weight times 1,000 to get your liters per minute. You can also correct for age and gender, as I mentioned earlier, using Astrand's equation. So it's fairly straightforward. If you want to do a little more work in this area, look at the Harvard STEP test that's been used for a number of decades now to evaluate workers for their ability to perform certain tasks on the job so they can be brought on. Remember, employees cannot be discriminated beforehand for being able to perform on the job. These are only evaluative tests, so it's very important to realize that you cannot discriminate based on these. These are tests in which one can be evaluated for performance and opportunities to work. Evaluation of muscular fatigue. This really hits home in terms of looking at that crossover from the safety side to the ergonomic side. Remember that a lot of times people think the ergonomics arena tends to focus on things that are more longer term and cumulative. People tend to think of safety as something that happens right now and is immediate, such as a cut or a laceration. But I contend to you that I strongly have seen and want to enlighten you that there is a continuum between safety and ergonomics, that they overlap, and this is one of the areas where it's very clear that you could have this issue come into play. So muscular fatigue is manifested by aches and pains, followed by reduced movement and weakening of the muscles. What happens is that you tend to recruit more muscles in order to do work. So for example, if you saw someone doing physically demanding labor with their hands and wrists, that if you were to come back later and watch that same individual doing work later in the shift, they may be recruiting the larger muscles of the arms and of the chest and of the body to perform the same job because the smaller muscles have become fatigued and they've recruited the larger muscles in order to help them complete the task. Lactic acid, and the amount of lactic acid in the muscle plays a role in localized fatigue. Obviously you don't feel that right away. Sometimes it's about 24 to 48 hours later that you really feel the lactic acid accumulate in the body. It can be very painful. It's most noticed in the larger muscle groups. For the whole body, heart recovery can be used. This is usually measured the first 3 minutes after work stops. So the idea is to stop work, let 3 minutes pass, and then begin to look at the heart rate recovery process as it goes down. In some instances, the heart rate will tend to increase after each recovery period, meaning that fatigue is starting to set in, and you need to pay attention to that so that you're not taxing the individual toward a point in which they'll have lactic acid buildup, but also fatigue that may set in that could possibly obviously impact them in a number of ways, everything from productivity to quality control to obviously safety issues. Phase 1 recovery. This is from the Bruja conference. If you look at Lucien Bruja, there's a tremendous amount of work done in this area in terms of understanding the physiology and recovery of individuals. Phase 1, heart rate in beats per minute during the second 30 seconds of the first minute. Phase 2 is the heart rate during the second 30 seconds of the second minute. And then phase 3 is heart rate during the third 30 seconds of the third minute. Now remember, when we're looking at this, we are looking at recovery after the third minute that the person has stopped working in terms of the recovery process. So if you're looking at 30 seconds, then you basically take that information, multiply it by 2, and that gives you the heart rate. This graph shows you how this works in terms of fatigue beginning to set in. So this is after one operation. This is the same individual. This is after 2 operations, and this is after 3 operations. And this is your heart rate count at 1 minute. This is 2 minutes, and this is 3 minutes. But you look, if you come back after the second operation, that peak here is at 120, and after the third minute, you're down to 90 beats per minute. But if you go over to the second one, after 2 operations, the same individual now has a peak of about 150. Then it comes down to a little over 130, and then it eventually comes down to about a little over 110 beats per minute. Compare that to the first period, and then if you look at the third period, you can see that the person now is up near 160 beats per minute. Period 2, 140, and period 3, about at 135. Notice that the angle is also starting to change right here in terms of recovery, where now this is starting to get a little more of a bend to it, meaning that you're not seeing a more linear reduction in the heart rate over time, that it's taking longer to recover. And if you were just to put these 3 series of data together, you can see that the person is not fully recovering from these operations, and that the fatigue is setting in because their resting heart rate is going higher after each of these operations involved. The relationship between heart rate, oxygen uptake, and total energy expenditure. I would like you to just look at the ranges right here. For example, heart rate beats per minute 90 or less in light work, all the way up to 160. In oxygen uptake, we're looking at 0.5 liters per minute to over 2 for extremely heavy work. Total energy expenditure in kilocalories per minute, 2.5 for light work, up to 15 kilocalories per minute for extremely heavy work. So I'd like you to just note these ranges right here, about 90 beats per minute to 160, from about 0.5 liters per minute up to 2, and from 2.5 kilocalories per minute to 15 kilocalories per minute. All of these ranging from light work, such as a typing task or doing some homework, all the way up to extremely heavy work, such as digging a trench. It's another table essentially showing you similar kinds of data for O2 consumption, energy expenditure, and heart rates right here, from sedentary all the way up to very heavy work, showing you similar ranges as outlined in the previous slide. So work rest scheduling then, this is a standard workload in the United Kingdom and the United States. It's equivalent to the workload generated for a man of average physique walking without carrying a load in a straight line on level ground at a speed of 4 miles per hour, or about 6.4 kilometers per hour. So an average man, let's say he's 25 years old, weighs about 65 kilograms, and is about 1.75 meters in height. If we were to look at that, and you can do the conversions here in terms of weight and height in the English system, But if you were to convert this in terms of energy expenditure, then we'd be looking at equivalent workload of about 370 watts, or about 5.3 kilocalories per minute for a 65-pound individual. Energy expenditure then, it's recommended total energy expenditure about 2,000 kilocalories during work as a maximum that can be expected for work to continue for months or years. Average energy expenditure about 4.2 kilocalories per minute during an 8-hour work shift. So this is our number that we're looking at here for an average individual, about 2,000 kilocalories per day. So that's the end of my lecture on work physiology and metabolism. The next lecture up, we'll be discussing heat stress. Thank you for your time and attention.